this video, uh, I'll be talking about some 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 philosophical intuitions, and before going into the details of those philosophical intuitions in quantum mechanics, I would like to go with some of the important postulates of quantum mechanics, and to start with, uh, the point is that this quantum regime, I mean, the subject itself, the quantum mechanics, it gives the revolutionary theory that governs the behavior of matter and energy at the tiniest scale, and has transformed our understanding of physical world. This this video provides a glimpse into the foundational principles and the key concepts that define the realm of quantum mechanics. So, to start with, uh, uh, the emergence of quantum mechanics in the early 20th century. It was as a response to the limitations of classical physics, uh, and it was pioneered by the contributions of visionaries like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. So uh, they tried to explain the departure from the classical physics. Now, the very first concept that I can talk about here is the wave particle duality. I mean, the duality of particle behaving as both waves as well as particles, uh, challenging the classical distinctions. The next important principle is the uncertainty principle that was given by Werner Heisenberg, and this principle that was given by Heisenberg, it gave groundbreaking concept that inherent uncertainties exist in measuring certain pairs of properties simultaneously, like position and momentum, like energy and time. And then the next important thing that we call as quantum states, and the superposition among the quantum states. So, describing the state of a system using wave function and probabilities. Now, the system is described in the form of wave functions, and wave function is a complex mathematical identity, and it doesn't have any physical interpretation or physical significance. And then what comes the solution? The solution comes in the form of probabilities. Now, this superposition principle, I mean, the phenomenon where particles exist in multiple states simultaneously. This is a very strong sentence. I mean, this is a very strong argument that when you calculate things in a theoretical fashion, you have a particle at many states at the same instant of time. So this certainly challenges the classical intuitions of an ordinary man. Uh, the next important uh, the next important root of quantum field is quantum entanglement, right? So the two particles can be entangled. I mean, particles become interconnected and influencing each other's states regardless of their distances. That means if there is an interaction between two particles at quantum level, and if the two particles are separated, one particle is at one end of the universe and another particle is at another end of the universe, they there is a kind of connection between these two particles. That means if we are in a position to measure something about the particle one, the outcome of the measurement that we have made on particle one will give us the complete information about the outcome of another particle, which is maybe on the edge of the universe. And this certainly uh, had implications when confronting the situations in the classical world, where everything was deterministic, where everything is deterministic, that we can predict everything about a particle. If we know the initial state of the particle, we can talk about each and everything about that particle during its passage from point to point. So in response to this quantum entanglement, there was EPR paradox, and this EPR paper that was published by Einstein, Podolsky, and Rosens, and they theoretically challenge it to the completeness of quantum mechanics due to entanglement, but because it seemed irrelevant, it seemed impossible in a domain where you can have two particles at infinity. Once they have interacted, they can still have an interaction. They can still influence each other, even if their distances are very, very large. So, uh, quantum measurement problems like wave function collapse. I mean, the mysterious process by which a quantum system's state is determined upon measurement. I mean, uh, once the measurement is done, once a measurement is carried on a particle which before the actual measurement has many probabilities being at many places at the same time. But once the measurement is carried out, the wave function collapses, and we are able to find a single particle. We are able to find a single particle. So there are diverse perspectives on what happens during the act of measurement. Including the Copenhagen interpretations and many world interpretations. Then another clause of quantum mechanics is quantum computing and information, right? So we can think of quantum bits, qubits, which is I should say an analog of bits that we have in classical computers. The computers that we have with whom the modern world is working, where we have all those informations, data, and all that being transformed from one point to another point. In all these computers, we make use of bits, right? But in quantum computer, we make use of qubits, and qubit is an analog of an identity that's being used in a quantum computer. Uh, uh, and is a fundamental unit of quantum information uh, that leverages a superposition and entanglements. So quantum computing, it's harnessing the quantum properties for exponentially faster computational processes. Uh, I mean, it's so fast that there is no match between the computations that a supercomputer can have with a quantum computer. There's certainly an exponential difference between the two actions. And what is so great about quantum computer is that 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 if we go back to the classical computer, we make use of only two bits. The information is there in terms of zeros and ones, but in case of quantum computation, but in case of quantum computer, you can have infinite number of states between the two uh, between the two states of a particle. Suppose if I take an example of an electron, that this electron has a spin angular momentum, and it has all probable values of spin angular momentum that can be exploited during computation, uh, which is totally a different kind of thing when we compare it with the classical computers, where we make use of logic 0 and 1. Here the logic extends from +1 to -1. There can be a long range of states that can be exploited in a quantum computer. So, so talking about the applications of quantum mechanics, I mean, nanotechnology is one of the emerging application of quantum mechanics, exploiting quantum phenomenon for advancements in material science and engineering. And then talking about quantum optics, this is another field where quantum mechanics is doing miles, utilizing quantum principles to study and manipulate light. And certainly ethics and philosophy should always be connected to the implications of quantum mechanics. I mean, we should examine the ethical considerations arising from unpredictability and indeterminacy of quantum systems. So there is another important version of quantum mechanics, and that is free will and determinism. I mean, philosophical debates on the implications of quantum mechanics for the concepts of free will and determinism, they keep on going on every platform, and this quantum consciousness, the role of conscious observer, exploiting the philosophical questions of the observer's influence on quantum systems, and the debates on consciousness. So considering how quantum mechanics interacts with discussions about consciousness, and quantum gravity, if you talk about quantum gravity, the quest to reconcile quantum mechanics with general relativity. The general relativity believes that gravity is not a force. It's basically a curvature between space and time. The objects fall uh, on Earth. They fall because there is a curvature. It's the curvature that makes things fall on the Earth's surface. It's the curvature that makes Moon to move around Earth. It's the curvature. Uh, the space-time curvature that makes the motion of planets around the sun. So, uh, there is always thirst. There is always there are always concepts that are tried to be generated and reconcile quantum mechanics with general relativity and understand the nature of space time. Then we have quantum technologies, ongoing advancements in quantum technologies with potential transformative impacts. This introduction that I have given. It's a small journey into the mysterious and counterintuitive world of quantum mechanics. It will prompt the exploration into the profound implications, philosophical questions, and cutting edge applications that continue to shape our understanding of the quantum realm. So, uh, so there are a long range of things there that are open, and no doubt this theory is not a complete theory. This theory cannot explain everything, but it explains that what we cannot understand. That system is sometimes uh, when you are in a microscopic domain, when you are in a domain of electrons, neutrons, and protons, uh, uh, they're the story there is very different. The Newtonian mechanics fails to explain the motion of an electron around the nucleus, because if we think electron as a classical particle, if we take it as a charged particle, then electromagnetic theory, the classical electromagnetic theory, tells us that when this charged particle accelerates, it produces electromagnetic waves. So if we take into consideration, say for example, an electron revolving around the nucleus, if we do that, we have a nucleus and electron is revolving around the nucleus. Once electron is revolving, that means electron's velocity changes at every instant of time. So when there is a change in velocity of an electron, that gives birth to the acceleration. That means electron revolving around the nucleus has acceleration. So if it has acceleration, it must radiate. It must emit electromagnetic radiations. So it must continuously lose its energy in the form of electromagnetic radiations and should fall into the nucleus. But doesn't that is not the reality of atoms. The electrons are revolving around the nucleus. So, so, uh, so there are many aspects where classical deterministic approach, the classical view, the classical calculations, the classical theory fails to explain this kind of problem where an electron revolving around the nucleus should continuously lose its energy and should fall into the nucleus. So uh, this is a domain where classical physics completely fails to explain why, then how this electron is there outside the nucleus. It should not even exist outside the nucleus when we think of the problem in a classical sense. So this the 20th century, it has certainly witnessed a scientific revolution that would define our understanding of the fundamental nature of reality, the birth of quantum mechanics, this historical um, uh, time that was there, because before the advent of quantum mechanics, uh, people had thought that things are clear out there, that we can go deep down to everything and can use the laws of classical mechanics to understand each and everything once we have the technology in our hands. But that was not the case once there was the advent of quantum mechanics. So now, if we go by point, say for example, a black body radiation problem. I mean, black body radiation problem. It was explained by Max Planck. What was the reality of this problem was that classical physics failed to explain the spectral distribution of a black body radiation. The classical physics had no solution for this problem to be explained, and the solution was given by Max Planck. And Max Planck introduced the concept of quantized energy, proposing that energy is emitted or absorbed in discrete units or quanta. Then the next important event is the photoelectric effect. So photoelectric effect was there. People were performing experiments, but they failed to explain the experiments. The experimental outcomes of photoelectric effect. They failed to explain that because the intensity of light had no influence on the ejection of electrons. Even if the intensity of the light was doubled, tripled, quadrupled, and what was observed experimentally was that the ejection of electron was somehow connected to the frequency of the falling photon. So this problem could not be explained on the basis of Newtonian mechanics. Newtonian mechanics failed to explain the problem of photoelectric effect, and this effect was explained by Albert Einstein, the man the man who was never comfortable with quantum mechanics, the man who was never who tried to write down the things in the form of the paper EPR and ER paper, uh, to oppose some of the peculiar outcomes of quantum mechanics, and this problem was solved. The problem of photoelectric effect was solved by Albert Einstein, and classical theory could not explain certain phenomena in the emission of electrons from the metals underlying that I was talking about. So the solution was given by Einstein, and Einstein proposed that light consists of discrete packets of energy called photons, revolutionizing the understanding of light and energy. Then Bohr model of the atom that I was talking about, that this model was given in 1913, and it classically the revolution of an electron around the nucleus could not be explained because it should radiate as per classical theory of electromagnetism. So Niels Bohr was the man who tried to answer this problem. So classical physics could not explain the stability of atom. And the answer to this problem was given by Niels Bohr, and he introduced a quantized model where electrons orbit the nucleus in specific energy levels, and and these levels are non-radiating levels. I mean, he postulated that electron does not radiate in these levels, addressing this way he could address the stability of an atom. Then another important event was wave particle duality, and the problem was the behavior of particles was inconsistent with classical description. It was inconsistent because if we go back uh, to the description of light. Light has dual nature. It could be explained when we talked about the double slit experiment. The light behaves as wave, and when it comes to explain the photoelectric emission, then we cannot explain this effect unless we assume that light is made up of some particles, some packets of energy, some quantas that was explained by Albert Einstein. So this the problem of the dual nature of matter, Lois de Broglie proposed that particles like electrons, protons, neutrons, they exhibit both wave and particle properties, and this laid the foundation for wave particle duality. Then another important principle, the only negative principle that we have in physics, we call it Heisenberg's uncertainty principle. It was proposed by Werner Heisenberg in 1927, and what was the problem? The problem was the accurate simultaneous measurement of certain pairs of properties was impossible. And the solution to this problem was given by Werner Heisenberg, and he gave the solution in the form of a negative principle. And what this negative principle was, that this principle states what we call as Heisenberg's uncertainty principle, asserting that there are inherent limits to the precision with which certain pairs of properties can be known simultaneously. So there is inherent limit. We cannot know it completely. When you take some pair of measurements that say, for example, momentum and position, you cannot be accurate. Even if you got 100%, you boil down all the errors around that system to zero. Hypothetically, even if the situation is like that, still the system will not give you the complete measurements. It is the intrinsic uh, property of these microscopic particles. Then Schrodinger's wave equation that he proposed in 1927. Uh, the Bohr model could not describe the complete atomic structure, couldn't completely explain the things. Where things were postulated in the form of non-radiating uh, shells and the integral multiple of angular momenta. So whatever the postulates that were there for Bohr model, the solution uh, uh, was given by Erwin Schrödinger, who developed a wave equation that described the behavior of electrons in atom, providing a more comprehensive and accurate model. And this certainly gave the birth to the quantum mechanics. All of these effects that I pointed out in a philosophical fashion, they gave birth to the quantum mechanics in 1920s, and the collective contributions of Max Planck, Albert Einstein, Bohr, de Broglie, Heisenberg, and Schrödinger combined into a framework of quantum mechanics, foundational mechanics, the principles of quantization, wave particle duality, and the uncertainty principle became central tenets of the new theory. And then, talking about nearly in 1927, Copenhagen interpretations. And Niels Bohr and Werner Heisenberg developed the Copenhagen interpretations, providing a philosophical framework for understanding the probabilistic nature of quantum systems. And the legacy of Copenhagen interpretations remains a foundational perspective in quantum philosophy. This context that I have tried to talk about, this framework that I tried to give some pasture about, its stages for the transformative period in the early 20th century, when the giants of physics reshaped our understanding of the microscopic world. The development of quantum mechanics marked a departure from classical notions in an era of profound scientific inquiry and discovery. So, with this, I would like to end this talk on some of the basic